memory. Computer memory is a collection of bistable devices. So they can represent only, say, a 0 or a 1 in each bit. And I think it's hilarious that I closed that dash with a end parenthesis, which is not what I meant to do. Organized as bytes. So memory is the actual physical things that it resides in are bistable, which means they can either be one thing or something else. They can be in either one state or another state. Okay? And they're organized as bytes, which are collections of 8 binary digits, which we abbreviate as bits. So we do this. Actually, I think we probably do this. I don't know. You could choose the I from either side. But I like to use the BI and then the TS. There's a little nice symmetry to that. Bits. Okay. There are 2 to the 8, or 256 unique bytes, because there are 8 bits in a byte, and there are 2 possibilities for each bit. So if you do the math, which is specifically 2 to the 8, you get 256 unique bytes. In more modern systems, each byte, so note well, not bit, of memory has a unique address or an identifying code. Okay? An important aspect of the C programming language is that it can deal directly with these memory addresses, a relatively low-level functionality. So those of you who have been boning up on C, which I hope you are, there are a lot of discussions around pointers versus variable names that are actually contain the contents of the address. So there's a difference between the address and the contents of the address. Okay, so that's part of why C is used a lot at this level, is that it gets really down into almost the hardware level interactions. Memory is not content specific. It can be used to represent numbers. So for instance, integers, floating point numbers, signed numbers, etc. Codes, for instance, character codes, numeral codes, etc. And instructions. We must keep track of the meaning of its contents. For instance, a single bit could represent the state of the union. 1 could mean covfefe, and 0, shithole. A less exciting example with 2 bits representing 4 directions would be, so if we have 2 bits, we have 4 possibilities, right? We have 1, 1, we have 0, 0, we have 0, 1, and we have 1, 0. So 4 possibilities, and we could say that 1, 1 represents north. 0, 0 might represent south. 0, 1 might represent east. And 1, 0 might represent west. Nobody knows what you've chosen for that bit to represent, or 2 bits to represent. So you have to keep track for yourself what they are. So let's talk about things you can store in memory. So the first and I think most obvious is pure binary numbers. So non-negative integers of different magnitudes can be stored as pure binary in memory. Here's an example of using 1 byte or 2 nibbles. So my spacing got kind of weird here, but these are all base 2 nibbles. So bytes, so 2 nibbles. We could start out with all zeros in binary, and that corresponds to 0 in base 10, all the way up to all ones, which in base 10 is 255. So 256 different non-negative integers that are represented, 0 through 255. So the non-negative integers can be stored, that it can be stored in 1 byte are 0 through 255, of which there are 256. But we can use more than 1 byte to store a non-negative integer in pure binary. If multiple bytes are representing a number, the byte that occurs first in terms of address in memory is called the most significant byte, or denoted MSB, and the byte that occurs last is called the least significant byte, or LSB. The most significant byte is usually represented as being to the left of the other bytes, and then the least significant is typically represented as being to the right because of the way that we do our positional number system. That kind of makes sense. I should also say that MSB and LSB are used for to abbreviate most significant bit and least significant bit as well, which has the same meaning. The most significant bit would be this one, and the least significant bit in this byte would be this one. You pretty much have to just know from context if somebody says MSB or LSB, what they're talking about, a bit or a byte. I will try to say, to do MS bits for bit, and I will try to reserve MSB for byte, most significant byte, but I probably will slip up because people just pretty much use them both to mean those two different things. Okay. Here is a list of the total number of possible non-negative integers that can be stored in n bits. Of course, the formula is 2 to the n, so we just pick out some typical values. So 2 to the 8 is 256, so in 1 byte. In 2 bytes, so 16 of them, 65,536. In 24 bits, which is 3 bytes, right? 16.7 million numbers. And 2 to the 32 gives us, is that 4 trillion? Yeah. 4 trillion. Billion. 4 billion. I'm not used to looking at numbers that big. It's kind of odd. 4 billion. Different numbers you can represent in 4 bytes. And if you have a 32-bit processor, this is where you're maxing out. It's right here. This is how many you got. If you have a 64-bit processor, you get to go up to 64, which is a longer number that I did not calculate because it was a lot more writing in commas, so I didn't do it. But also, our processor only goes up to 32. So we have a 32-bit processor. Our Cortex A9 is a 32-bit processor. So that's what we got, which isn't bad, but also you always are going to have some precision that comes in when you have just that many different possible numbers. Okay, very good. So 8-bit 2's complement signed binary. So that we just did pure binary. You can store that in memory. Also, you can store 8-bit 2's complement signed binary. How can a negative number be stored in memory is the question that leads to this representation. So a single byte can store 256 unique pieces of information. For decimal numbers, this can range 0 to 255, or say negative 128 to 127 positive 127. So you could, instead of going from, you know, if you have your number line here, instead of just going from 0 to 255, you have this many possibilities. You could just shift this over and go from negative 128 to positive 127, and you have the same number of them, but you're representing different numbers with your with the same byte. Okay. A very convenient binary representation is called 2's complement. A number x has 2's complement in n bits of 2 to the n minus x, represented in base 2. That is the number of unique numbers representable minus the number represented in binary, which is a little hard to parse, which is once again why we do an example. For instance, the 8-bit 2's complement of 0110100 is, you take the total number that you can represent in 8 bits, which is 2 to the 8, which is represented, which, remember, 2 to the 8 minus 1 would be 1, whatever, however many ones, 8 ones. And then you overflow it by 1, and you get 1 with all zeros. So you do this subtraction, and you're going to get the 8-bit 2's complement number. So this subtraction proceeds as follows. 0 minus 0 is 0. 0 minus 0 is 0. I'm liking this so far. All zeros. And then 0 minus 1, oh no, what do? We got to borrow, but dang, so this 0 has to turn into a 1. This 0 has to turn into a 1. You have to keep going. This 0 has to turn into 1. This 0 has to turn into a 1. This one goes to 0. Okay. So now you have 2 minus 1, which is 1. And then you have 1 minus 0, which is 1. 1 minus 1, which is 0. 1 minus 1, which is 0. And 1 minus 0, which is 1. So that is the 2's complement representation. Below are listed some 8-bit 2's complement decimal interpretations. So let's look at these. So if we start off at 0, so all zeros in binary, this corresponds to 0 in decimal, right? Just like before. And 1 in binary is 1 in decimal. And as you keep increasing, so this is the same as before, right? All the way up to 127. So before you overflow to that last bit, it's completely the same as your good old-fashioned regular binary, right? Your pure binary, we called it. Now, once you overflow to that last bit, you add 1 on the binary side, the representation in 2's complement, if you were to take the 2's complement of this guy, this is going to, sorry, not take the 2's complement of it. We use this to represent negative 128. So we go from positive 127, and then you add 1 in binary, you overflow that to that last bit, and we're going to say that actually corresponds to negative 128. And then we're going to count up. We're still counting up, right? We're counting up from 0. But it's like if we looked at our number line, we started out counting up from 0 all the way up to 127. And then we went, whoop. Maybe we should dash this line. We dash this, we skip all the way back to here, and then we start counting up from negative 127 up to 0. So you don't actually get to 0 because 0 is where we started. So yeah, that's how we represent it in binary.
Does in binary have negative number?
So that's what we're doing here. That's what we're representing. So we're saying that these are negative numbers. You could interpret them as pure binary, but we're going to say that sometimes we've encoded into these binary representations a negative number that has this this convention to it. So it's as if in Pac-Man, starting from the middle and exiting screen right, only to appear screen left, counting up loops one back down to negative numbers, right? You guys played Pac-Man, right? Okay, good. If you haven't played Pac-Man, you can play it on the internet for free. I think Google even made a little thing. You can play Pac-Man. Classic video game. Gotta play it. It's fun for like a few minutes. I think back in, you had to be there for it to be as fun as people thought it was, but like, I don't know, maybe when you're in an arcade.
There's a whole Pac-Man fever thing. People are crazy for that.
I don't really get it.
The record on that thing all the time.
But that being said, we can obsess over pretty much anything.
Yeah, that's true.
I mean, look at the Tide Pod challenge. That's the thing.
It's crazy.
I can't believe that's a thing. Unbelievable. Okay, so note that positive 2's complements are the same as their pure binary counterparts. It's the negative ones that are different. So there are two more convenient ways to find the 2's complement. Instead of doing 2 raised to the number of bits, subtracting that like we did over here. So you can always go back to this definition, do the subtraction. But there are 2 ways that are a little bit easier, I think. Way 1 is to switch all the bits. So everything that's a 0 turn into a 1, and everything that's a 1 turn into a 0, and then add 1. And you get the 2's complement. So I think that's a pretty easy way to go. Another way to go is this is like really basic, starting from the right, copying all the bits through the first 1 encountered, then switching all thereafter. So it's kind of nice. Both methods can be seen to always hold from the subtraction definition. So we can use that if we want. I don't really have strong opinions on which way you try to use, but let's try them out on this example. But first, the 2's complement of the 2's complement of x is x, which is part of why the 2's complement is used as a representation for negative numbers. Yeah. So find the 2's complement of 0, 0, 0, 0, 0, 1, 0, 1. Okay? So let's take... Which one do you guys want to use? We already did the subtraction one, so let's use one of these 2. Which one do you guys prefer?
First one.
The first one? Okay, let's try the first one. So we switch all the bits first. So 1, 1, 1, 1, 1, 0, 1, 0, and then we add 1. So plus 1, and this bit just turns into a 1, right? So we get 1, 1, 1, 1, 1, 0, 1, 1. So that's our 2's complement. Well, we have enough space. Let's just do the other one too. Might as well. So this one, we just immediately write it down, right? So we copy from the right through the first one encounter. So the first one encounter is actually the first bit, right? So we copy the 1, and then it says switching all of them thereafter. So the 0 turns into a 1, the 1 turns into a 0, and then the rest of them are 1s. Because we switch all the bits. So anyway, they're all like, there's just like little tricks, right? To get you there a little bit quicker, but they work. So if a binary number is interpreted as a 2's complement binary number, it is negative if its most significant bit is 1. So you may have noticed that over here, it's that when that last bit gets occupied, then we start to interpret them as negative. So you can tell if a 2's complement binary number is negative by just looking at its most significant bit. See if it's 1, it's negative. If it's 0, it's positive. So, yeah. Pretty cool. All right. Now we're to the binary coded decimal. So we can represent good old-fashioned binary, what we call pure binary. We can represent binary, 2's complement binary, and in memory. And we can also store binary coded decimals in memory. So a binary coded decimal represents each decimal digit with a nibble. So a series of nibbles can represent a decimal number. This leads to slightly less dense storage because each byte or each nibble could contain more information than just those digits, but you're sacrificing that for precision. So this leads to a slightly less dense storage, but it's still useful for high precision computation. So BCD for rounding error. So recall that the number 421.73, God, that number. I don't know why this survived. It doesn't really need to have this big thing that says problem. Recall that the number 421.73 had an infinitely long binary representation in that example that we did. Represent this number in BCD. And we are going to find that we can do that without having to chop off any digits, which is nice. Let there be an implied decimal point, as some encodings define, between the third and fourth nibbles. So we're gonna kind of ignore the details of it. There are different encodings that define where the decimal point is defined, but suffice it to say that there are some times where it's specifically between certain nibbles, or there's another possibility is that you can have one nibble that tells you between which nibbles the radix should be. So, okay, so how do we do it? What do you guys think? The idea here is to take each of these digits, the 4, the 2, the 1, the 7, and the 3, and represent them as a nibble. So the 4 is going to be 0, 1, 0, 0. So that's a nibble, right? Four bits. So the 2 going to be 0, 0, 1, 0. The 1 as a nibble is going to be 0, 0, 0, 1. 7 is going to be 0, 1, 1, 1. And 3 is going to be 0, 0, 1, 1. So you could write these all out in a string, or string them together in a long format if you wanted to, but essentially a sequence of these nibbles, from this nibble to that nibble to this nibble to this nibble to this nibble, is a binary coded decimal. So that allows us, I mean, like it took 5 nibbles, which is actually more than more memory than we can actually encode more information in those 4 nibbles than we are encoding. And the reason is that 2 to the 4 is equal to what?
16.
Yep. 16, but we're only representing 0 through 9, which is has length of 10. So we're leaving 6 on the table here. So you can use one, like for instance, you could use, so you have an extra 6. You could use one of them to be like a decimal if you wanted to, decimal point. You could use them for other purposes as well, like telling you how many nibbles are to come after this, that type of thing. Yeah. So sometimes they have some actual representation in a given encoding. Sometimes there's actually something that we can use that for. Other times it's just wasted. So it's important to keep in mind. But that's the idea. I mean, so you can represent this decimal number exactly. It costs you a little bit in your density of memory, typically. Okay. Which brings us to floating point numbers. They can represent very large or very small numbers with limited space. Great. That's exactly what we wanted. It is for computer memory what scientific notation is for a small piece of paper. That is, it represents a number as a mantissa, x, and an exponent, n. That is, x times 2 to the n, where we have used the conventional base of 2. So scientific notation would say x times 10 to the n. In floating point, typically this is 2. The base is 2. But the idea is that, you can represent the important part of the number in the mantissa, and then you can scale that up and down significantly by putting it in the exponent. So making the exponent like 5 would be 2 to the 5, which is could scale it significantly. So it's kind of a nice short way of writing something that's big and making it compact in memory. So consider the following illustration of a 32-bit or 4-byte floating point representation. So we have 4, so I'm representing each block here. Each block is a byte. So you often will have a 1 byte that's reserved for the exponent. So in 1 byte, you have 256 different possible exponents, which covers quite a bit of ground, right? Usually you're going to make it a signed binary number, so you can go from positive 127 to negative 128. So pretty good range there. And then 24-bit fractional signed binary mantissa. So you have 3 bytes to represent the part of the number that multiplies the exponential. So pretty good. Obviously 64-bit is better. You get more bang for your buck, but 32-bit's not bad. we would interpret this as, for instance, so that the 24-bit mantissa, we assume the radix point is at the far left typically. Unlike in scientific notation where you do like 2.3 blah 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 times 10 to the something, we always have the decimal point on the far left. We typically do for a floating point number, just as a convention. Could have been anything, but that's what was chosen. Okay. And then times 2 to the 8-bit exponent. Yeah. Does that make sense?
Mm-hmm.
Pretty cool. I mean, you probably heard the term floating point quite a bit, and you may have wondered what that meant exactly. I mean, you kind of knew it was something to do with like fractional decimal numbers, right? But like, yeah, so now this is what floating point is. And we represent a lot of stuff in floating point. So as engineers, I would say the vast majority of the numbers that we use are floating point numbers, although we do use integers a lot, and we will occasionally have need in super high precision computation of doing binary coded decimal, so that we don't lose anything. Because this has 24 bits to fit it all in, and typically this is not going to be a binary coded decimal. I mean, you could technically have a floating point that was a binary coded decimal and an exponent side, but I've never seen that. I'm not sure. Maybe people do that. It'd be weird. Be cool though. Okay, character codes. In addition to numbers, memory can store character codes, which are encoded, alphabetic, special symbols, emojis, etc. So the most common character code is the American Standard Code for Information Exchange, or ASCII. This is how people say it. It's a 7-bit code. So there are 128 unique character codes. It leaves the 8th bit of a byte, called bit 7, because there's bit 0 through bit 7, the parity bit, to be checked for transmission errors. It works as follows. Set, which means to turn to 1, a reset, which means to turn to 0, before transmission, such that the total number of set bits is either even or odd. If the system is using even parity, an even number of bits are set, or if it's using odd parity, an odd number of bits are set. For instance, under odd parity, if the byte 11001101 is sent and the byte 11000101 is received, with its even number of set bits, the receiving system knows there has been a transmission error. So the sender and the receiver have to agree on what the parity is going to be. So if it's odd parity, then it's going to, before it sends something, it's going to see how many ones show up. If there's so how many ones show up in this part. If you're doing odd parity, it's going to set this last one to make it even or odd. So in this case, 1, 1, 1, 1, there are 4. And so we're using odd parity, so they set that bit to that parity bit to 1, which makes the total number odd. Sends it off. The receiver knows that when it receives this byte, that the total number of set bits should be an odd number if it's been sent correctly. And it gets this guy. It doesn't know which one's wrong. I put the 0 there in red just to show us that the 1 turned into a 0. It doesn't know which one's off, but it knows that there must be one that's off because there are 1, 2, 3, 4 ones in this byte, and that's an even number of ones. So it knows that the sender would have made sure that there was an odd number before sending. And you might think, well, but what if there was an even number? What if it wasn't 2 bits that were off? Or what if it wasn't 1 bit that was off, but it was 2 bits that were off? Yes, that could happen. And so the motivation for this is that the probability of having 1 bit being mistransmitted and received is actually quite low in most of these communication systems. And if it's quite low for 1 bit to have that flip, it's astronomically low for 2 bits to get flipped in the same byte. So that's how the parity bit is actually effective. So yeah, it's kind of cool. I mean, it's like, it's clever. It's not perfect, but it's clever and cool. So sometimes I just wish they would have just given us, twice as many ASCII characters instead of this parity bit.
So how do 2 computers decide between odd and even parity?
It becomes part of a communication protocol. So you can have communication protocols that are always odd parity for everything in them. You can have communication protocols that say that the first byte that you send should set the parity for the remaining. You can have different protocols depending on the system, but that's why they define these communication protocols so that people who are working at different companies on different systems can communicate between their products using the same communication protocol. So as long as everybody follows it, it's fine. So sometimes it's due to like the USB standard, or it's due to serial bus standards, or whatever it is. So it's really it's very much dependent on the situation, but essentially it comes down to a convention that's set by some communication protocol. I mean, yeah. I don't really know. I mean, to me, when somebody thought of this, they could have triumphantly just said, humans will use odd parity or even parity, something like that. And everyone always would do that. Instead, we have to know, which, I mean, in theory, I mean, neither is better. So I don't know why you would use one versus another. I don't think there's any advantage. I can't think of a possible reason why there would be an advantage. But maybe they wanted to leave that open. Sometimes things are more interesting when they're harder. I don't know. Okay. Which brings us to our last thing we could have in memory, which are instructions. Instructions are codes that direct the operation of a microprocessor. We talked a little bit about instructions when we first talked about computer architecture. The MyRio has an ARM Cortex A9 processor with 32-bit instructions. That is, with 32-bit instructions, you have the possibility of 4 billion whatever instructions. Thank God they don't have that many. But the manual for this processor, I think I mentioned, is like 2,700 pages long. So the instruction set is pretty big. Not that big, but it's pretty big. So, okay, memory interpretation. Suppose the following, this is just sort of like to round out our discussion. Suppose the following is stored in a byte of memory. This binary number. Or in hex, it would be D5. How might this be interpreted? What do you guys think? Depends, right? Depends on what you put in there. You don't know what it's supposed to represent unless you know what you were trying to represent when you put it in there. So that's why if you find somebody's encrypted drive, you can't just look at a byte. You could read all the ones and zeros. That's fine, but you have no idea what it's supposed to represent, so you're totally screwed. You have to know what you put there in order to be able to read it. So, for instance, so possibly, it could be just a pure binary number, which would mean that if we were to represent it in base 10, it would be 213. That may be what you meant when you wrote that byte. You also could have meant maybe it was supposed to be an 8-bit 2's complement signed binary. In which case, we look at this thing, the first bit is a 1, so what do we know? It's negative. It's a negative number. If we convert it into base 10, it would be negative 43 in base 10. It's also possible that it was a binary coded digit with 2 nibbles, which would be the first nibble, though, is actually an illegal nibble because it corresponds to, let's see, 8, 12, 13, right? 13, which isn't 0 through 9, so it's illegal. So it could represent something in some specific encoding of BCD. So I'll say is illegal unless there was some specific encoding for it. And 0101 would correspond to 5, right? Okay. What about ASCII? Maybe with odd parity, because 1, 2, 3, 4, 5. So if you look up the ASCII character for this, which in one way to look it up, so looking up with the 7 bits is fine, but it's also kind of hard to look at. So oftentimes you look up an ASCII character in terms of the hex representation of those bits, which is 55. So that would give us the letter U. So the character capital U in ASCII. Or, final one, it could just be an instruction or often we'll call these things opcodes. And there are obviously more possibilities than this too. These are just some possibilities. It could be part of some larger piece of data that we're only getting a little bit of. Like it could be a 2's complement, but it could be like a 16-bit 2's complement, and you might just be looking at half of it. So, yeah. So it's important to keep that in mind, is that you have to know what you put in memory there in order to have it be meaningful. Okay. And then finally, we'll We'll talk a little bit about the physical characteristics of memory. In addition to speed, volatility and cost that we talked about in lecture 1.3, there's another important aspect of memory, and that is rewritability. This defines memory into two categories: read-only memory, of which the state cannot be altered. Put cannot into quotes there. Only detected by the CPU. So it's a sort of read-only in terms of the CPU. You can often erase it and rewrite it, but only under specific circumstances or a limited number of times. So read-only memory is called ROM. You guys probably heard about like your ROM, like flashing the ROM on this device or whatever. It's something that you can rewrite sometimes under specific circumstances, but is not generally done. Versus RAM, which is a memory that can be both read and written to by the CPU. There are several types of ROM described as follows. ROM is just ROM by itself, is masked ROM that is programmed at manufacturing and cannot be altered. It's for mass production and is cheapest. So you just do it once, and there's just no way to interface with it really to rewrite it. Super cheap, but better get it right the first time. Otherwise, you can't do a patch update later on. It's done. PROM is field programmable. That is, it can be programmed after manufacturing, typically only once. So maybe you have one field setting programming opportunity. You set it, you program it, and that's really your only access to it. You don't really have any more access to it. EPROM is erasable, usually with UV light, and reprogrammable after manufacturing, but has a short number of erases on the order of 100 times. So you might be able to erase it several times. Like for instance, if you had to like patch the ROM on something that you thought, well, I might need to do some patch updates, like, you know, a handful of times. I don't need to read and write from this memory millions of times. I just need to read and write from it like a handful of times when I want to, say, change how this thing boots. Like, very rarely will you need to do that, but there might be a need to do it a little bit. And then there's the electrically erasable and non-volatile EEPROM, or EEPROM, is often called flash memory. So that's the stuff that we use as longer-term non-volatile storage, but can be rewritten as well. Yeah, so on a lot of embedded devices, you'll see this type of ROM. So it's non-volatile. It'll store things like programs that run on boot and that type of thing.
Is that the same as like flash drive?
Yeah, it's the same technology that underlies it. So the flash drive is something, I mean, it's more of a peripheral device in the way that we interact with it most of the time. But that same stuff can be on the board and would be interacted with as EEPROM. And so, like, for instance, an embedded computer motherboard might include some of that has, like, the boot instructions when it gets turned on. And so it needs to be able to have access to something that's non-volatile. But also you might want to change that sometimes. And so being able to change it electronically without having to have another device to do the flashing of it, it's nice. So you can do it. You can do like patch the BIOS stuff electronically and not have to like take it physically out of the device. So it's becoming more and more common. A lot of like the little boards that you buy now will have bigger and bigger amounts of it. I mean, it used to be like 256K was the flash memory on the board. Now, but it doesn't always have to be big, though. I mean, it might really just be like a couple megabytes because that might be all you need, and why pay for more? So, yeah. Okay, memory organization. In memory, bits are grouped into bytes of 8 bits. Okay, so we already kind of mentioned that. Each byte is often considered as 2 nibbles, the contents of each represented by a hexadecimal numeral. For instance, a byte might be represented as follows. So 1, 1, 0, 1, 0, 1, 0, 0, with the nibbles a little bit of room between them. And we would say, oh, well, this over here in hex is D, and this over here in hex is 4. So you could represent the byte of memory in binary like this, or you could represent it as hex, which is probably more common to see, is the hex representation. Each byte is given a unique positive integer address, distinct from its contents. So it looks like this. So you have a byte that has an address, and you have another byte that has an address, and another byte that has an address. And the contents are associated with the address. So you have to be able to know both about it, where it is in memory and what's in it. When storing a multi-byte number, so one number might be represented in 2 bytes, like, so say maybe this byte and this byte. Maybe it crosses from this byte over to this byte. We use the big endian convention. So that's what we'll be using. There's also another one, but the big endian convention is that the most significant byte is stored at the lower address. So this would be MSB, and then this would be LSB. So it starts at the lower address and goes up. Little endian stores it the other way, so that the most significant byte's the higher address, and the least significant byte's at the lower address.
What do they mean, high and low address?
So the address here, there's some integer representation of them. So there's an order to them. So that, like, this is a lower address, this is a higher address. So I would say low, high. And we have to know if a byte is going to go, or if a piece of data is going to cross bytes and be represented in multiple bytes, then we have to know if this byte comes first or this byte comes first. We need to know which one is the first byte associated with that number. So you have to either have the convention that it goes from low address to high address, which is the big endian convention, or that it goes from high address to low address, which is the little endian convention. We're going to be using the big endian convention, but people do use the other one too. So, oh, there's an L in little. L, little endian. Yeah, so big endian, little endian.
Not Indian, Indian.
Endian, that's correct. Yes. Yeah. And so that is all I had on this lecture. Any questions on that specifically? It's a lot, right?
Yeah.
I know.
Do a lot.
It's so much. It's so much. I was writing up these notes, and I was like, oh my God, there's so much to say.